also do the key exchange with Diffie-Hellman instead of RSA. So the handshake can be done with Diffie-Hellman instead of RSA, and it's actually even more common today, and we'll see in a moment why. It gives you an extra security property. So here's how it goes with RSA, with Diffie-Hellman. So the Amazon server is going to send their Diffie-Hellman information signed with the Amazon key. So here we're using, again, you can use RSA if you want, but we're not using RSA to encrypt the PS secret. We're using RSA to sign the Diffie-Hellman information. Someone is typing and I need to mute themselves. Thank you. All right, so the Amazon server basically derived A, which is the secret key for Amazon, chose it at random, and then they send the Diffie-Hellman information signed with the key of Amazon. Someone is again typing, so please mute yourself. Okay. All right, so the first question is, how can I, remember Diffie-Hellman was suffering from a man-in-the-middle attack, right? That there could be an attacker here, and the attacker could send on, their own Diffie-Hellman information. So instead of G to the A, it would send G to the attacker secret. So how can we prevent this here? Any ideas? Or how is it prevented already? Can someone raise their hand? Caroline, do you want to unmute yourself?
I feel like this would be kind of basic, but like maybe by computing a MAC over like the specific information to show that it's from Amazon and not from an attacker.
So what are you going to compute over that information?
So maybe the secret key and with the particular random it was.
Yeah, so how are you, so that's a good idea of using the secret key of Amazon. How exactly are you going to use it? Or is it, how are you making sure that, for example, what if it were signed by, see, this tuple is signed by Amazon. So if the browser were to know the public key of Amazon, then they could really make sure it's not coming from an attacker. But maybe that, but what if the attacker is signing with his own key? How can the browser make sure it has the correct public key for Amazon? Anybody have ideas? Maybe raise your hand. Nicholas?
The browser already has the public key from the Amazon server from the cert that it just sent, and it can verify that that certificate is legitimate for, say, Amazon.com. So it can just verify the certificate. It can just verify the signature on the Diffie-Hellman parameters sent by the Amazon server signed with their secret key. Right,
exactly. So because of this certificate, and the browser checked the certificate before, the browser has the public key of Amazon. Now, when this Diffie-Hellman information comes from Amazon, signed by Amazon, then the browser can use that public key of Amazon to check it. So this is how the man-in-the-middle attack is prevented. It's because the Hellman information is being signed by Amazon, and the browser knows the public key of Amazon from a certificate. All right. So this is this. Okay. So let's see more concretely what happens before the handshake. So before this green lock, the Amazon server generated random A, the browser generated random B. The Amazon sent the public key in Diffie-Hellman to the browser. The browser verifies the signature and makes sure that it it verifies with the public key of Amazon from the certificate. And then it computes this pre-master secret. So here it's different than for RSA, the previous RSA scenario, because it's not generated at random by the browser, but it's computed in this Diffie-Hellman way. And then it's sending this public key information for Diffie-Hellman to the Amazon server, and the server generates PS as well. So note that an important difference here is that the browser is not sending PS encrypted to Amazon server. It's just sending the Diffie-Hellman information, which the server uses to create PS. Okay, so both the server and the browser are generating PS. But you might worry about the attacker, man in the middle, attacking here, right? And TLS is supposed to be end-to-end secure, so you can't have a man in the middle in TLS. So you might worry about an attacker here who is going to change this information so the Amazon server gets to create a different PS. How is this going to be detected later? Any ideas? How is it going to detect later that the browser computes a different PS? Sorry, that the server computes a different PS from the browser. So again, if the man in the middle changes this quantity to be something else, then the browser is going to compute a different PS. The question is, how will the two of them realize that the PS that the browser computed is different from the one that the server computed? Anyone wants to raise their hand? So I'll ask the question again. So basically, the question is, if some man in the middle attacker changes this quantity, then that makes the server compute a different PS than the one it should, and the PS won't match the PS of the browser. And we've seen already a mechanism by which they can later tell if they have agreed on the same cryptographic material or not. Does any of you remember what that was? So raise their hand. Okay, so someone is writing in chat, Mac, the messages so far. Yes, that is very much true, Mac, the messages so far. Please though, raise your hand and say it loud because I can't check the chat at the same time. So yeah, so Nikki's suggestion is true, is that later you're doing the same procedure as before of generating the cipher keys and the MAC keys from the PS, RB, and RS. Now, if the browser and the server have different PS, then the integrity keys will be different between the two of them. So they will detect that when they do the MAC of the dialog at this point, right? The MAC will not verify on the server side because the server has a different MAC key. It doesn't have IB, it has IB prime because it used a different PS to generate it. And similarly, the browser will realize that because the server used an IS that's different from the IS the browser sees, because these are all generated from PS. So it will be detected later. So we are not so concerned about this piece being modified because it will be detected later. And then the rest of the interaction is the same as for the RSA key exchange. So basically, if you do TLS with RSA or with Diffie Hellman, the only thing that's different is up to here, up to how you generate the PS and you share it with Amazon server. That's the only difference is here. After the PS is shared, things are happening exactly the same way. Any question? So Ian is asking, so generate both cipher key and MAC integrity key with PS. Yes, we do that. We generate both of them from the PS, RB, and RS. Both the symmetry keys for encryption and the MAC integrity keys. Nicholas, you raised your hand. You have a question?
Yeah, I just wanted to ask, so since the Diffie-Hellman also includes like the private A and the private B, which I presume would be generated randomly, does it technically still need the client and server random if they were to use this key exchange as opposed to just encrypting the pre-master secret?
That's a very interesting question. So the question is, do you still need, are you asking about both randomnesses or any one of them in particular?
Well, because it seems like now both the server and the client have their secret Diffie-Hellman key, their secret Diffie-Hellman A and B, which would both be generated randomly, I would assume. So I was just wondering if, like, technically we still gain anything in addition because of the client and server random.
Yeah, so you can still worry about replaying, right? So let's see what you could replay here. So Amazon server sent you this information, and what if you are to replay I see. What if you are to replay Amazon's, what if you are to replay Amazon's message and then you replay the browser's message, right? Then you are establishing again an old connection with the old keys. So there's still some form of replay. Maybe those keys were compromised somehow, right? Somehow the attacker managed to compromise the keys and he just really wants to get them to, yeah, I mean, I agree that if both of them choose this randomness correctly, then I agree with you that I also don't really see why you need a random, if they both choose it correctly. I guess it's more of a redundancy aspect. Because also if you generate initially the PS correctly in the RSA case, then it's not clear that you need the, yeah. So I guess it's a redundant thing, but I agree with you. A and B are already randomnesses. Completely agree with that. All right. So Lily, do you have a question?
Yes, I have a question. So when we're verifying the MAC of the dialog, are the integrity keys different? And if so, then are we verifying that the MAC is supposed to be exactly the same between the two?
Yeah, good point. So exactly. So here's what happens. So the dialogue is everything that was exchanged between the two all the way up to here. And so both of them can compute this dialogue deterministically, right? Moreover, all these keys are also generated deterministically from PS, RB, and RS. Okay, so all these keys are generated deterministically. And so both of them have the same dialogue so far, unless the attacker was in the middle and made them see different things. But if the attacker didn't tamper with anything, they both see the same dialogue and they both have the same keys. Great. So now the browser is going to MAC and send this MAC over. What Amazon is going to do the same thing. It's going to MAC the dialogue so far using IB. IB is the key that the browser is supposed to use, but Amazon server also has it because it generated it from PS and the randomness deterministically. So then the Amazon server by itself alone is going to MAC the dialogue so far using IB and check that this value is the same as the one received from the browser. If it's the same with the one received from the browser, it means that the two of them have seen the same dialogue so far, the same, and that the integrity key is the same. Now look, if the integrity key is the same, all the other keys are really the same. Why? Because you generated the integrity key from PS, RB, and RS. These were the seed using a pseudorandom generated as deterministic. So if IB is the same, then with very overwhelming probability, all the other keys are the same. So then Amazon server knows that, okay, I really established a successful TLS connection with the browser. Now, the browser needs to check the same thing as well. The browser needs to be sure that Amazon server is seeing the same cryptographic material. So it does the same thing. It MACs the dialogue up to here, MACs the dialogue up to here, and then it uses the integrity key for the server IS, and it checks that it matches the value received from the Amazon server. And then it can be sure that they agreed on the same thing. Does this answer your question, Lily?
Yes, so then the integrity keys between the browser and the server, as well as the cipher keys, are very likely to be the same. Just to clarify.
Yes, the keys of the browser and the server are the same. What do I mean by that? So each one of them is going to generate 4 keys. The browser is going to generate these 4 keys, and the server is going to generate these 4 keys. Now they're generated deterministically from PS, RB, and RS. How? Well, use a pseudorandom number generator where these 3 are the seed. Okay, so then it's going to generate each one of them are going to generate these 4 keys, and they're going to be exactly the same 4 keys. Now, the browser will use the B keys when it sends data, and the server is going to use the S keys when it sends data. And again, it's because you want to prevent replay, right? If you send something from the browser to the server, you don't want someone to kind of send it from the server to the browser. Does it make sense?
Yes, thank you.
Okay, great. Any other questions? Okay, okay, so Howard, do you have a question?
Yeah, sorry. I'm also just reading the chat while you're talking.
Yeah, that's hard for me
So
to keep
just to be
track of.
clear, to clarify,
Mhm.
CB, CS, IB, and IS are all distinct keys, right? It's just that both the server and the browser possess all 4 of those keys.
Yeah, they're
like-
distinct keys. So imagine you take
okay.
imagine you take up pseudo random number generator and you seed it with PS, RB, and RS. That's one string. You seed it with that, and it outputs a long string of random bits. The first piece is CB, the next piece is CS, next one is IB, and next one is IS. Okay, so there's 4 different keys, and each one of these 2 parties have them. They have all the 4 of them.
Thanks.
And now the browser is going to encrypt using the CB key, and MAC using the IB key. And then the server is going to decrypt and check the MAC with those keys. But the server is going to send encrypted with the server's keys, CS and IS. But they both have them because it's symmetric. It's a symmetric key scenario, so they both have to have them.